Hello, sorry, there was an interruption. So we continue from where we stopped. Okay, yeah. So I said that the force on AB pushes it down while the force on CD pushes it up. Rotation. Just a minute, please. Thank you. So the force on AB pushes it down while the force on CD pushes it up. So it's like kind of rotating the coil. The split rings or commutator reverses the polarity and current each half cycle. So the coil rotates continuously. So what we mean to say is that the force pushes this part down, this one goes up, and on like that. So it keeps rotating that way. So in a real motor, the rotating shaft is called the armature. The rotating shaft is called the armature. There's another worked example here. It says calculate the induced EMF in a 120 centimeter squared circular coil having 100 tons when the field strength B passing through the coil changes from 0.1 to 0.001 Tesla in 0.1 second at a constant rate. This is also to be done as a class work, and I would like you to also try this out and send your solution as a message. So the current through the armature coil interacts with the magnetic field B to cause a torque, what is called a torque, given by this equation. And the torque is produced on the coil, which rotates, and the torque rotates the coil and the axle. The theta, there is sine theta there. N is the number of turns, I is the current, and the sine theta is the angle, A is the area, of course. Theta is the angle between the field lines and the perpendicular to the plane of the coil. And so I want to sorry, I'll take that again, that A is the area of the coil and N the loops. The torque always rotates the coil in the same sense. Therefore, average torque is equal to constant times the magnitude of the torque of the product of the number of turns and the current and the area and the magnetic field. Okay. A back or counter EMF is induced in the coil. This back EMF opposes the voltage source that drives the motor. Hence, the net potential difference that causes currents through the armature is given as net PD across the armature equals to the line voltage minus the back EMF. Therefore, the armature current is equal to the line voltage minus the back EMF divided by the armature resistance. And the mechanical power that is developed within the armature of a motor is given as P equals to armature current times the back EMF. Another worked example is shown here. And in a motor, a conductor, all these worked examples are also part of your tutorials eventually. So you write them down and try to work them out based on the formula given for each of the worked example. And during the week of revision, I think there will be a week for revision, we will discuss each of them, okay? Maybe I'll give you a solution, I might give you a solution to each of the worked example. But for now, you try each of them and let's see how far you can go. You can send the solutions, like I said earlier, as a message. But during the revision, week of revision, we'll look at these worked examples one after the other. So there is this one, which I hope you have written down. In a motor, a conductor of 120 millimeter long carries a current of 2 amperes. If it lies perpendicular to a uniform magnetic field of 1.4 Tesla, what is the force on the conductor? What torque is produced if the conductor is 50 millimeters from the axis of the motor and parallel to it, and the field points from the axis to the wire? So I expect that you have written this down and that you will solve it and send the solution as a message today, within this lecture period, if possible. So this is the second worked example under that. It says a motor running at full load on a 118 volts line develops a back EMF of 107 volts and draws a current of 6 amperes through the armature. What is the mechanical power output of the motor, disregarding frictional losses? What is the armature resistance? I'll give you a minute to write this down because you are supposed to send the solution. Is it being recorded? By them too. Okay. So put this down in your notebooks and try it out. Excuse me. So I'll take your question. What are you raising your hand for, John? I'll take it at the end. Please don't interrupt now. So we go on to electric generators. Machines that convert, electric generators are machines that convert mechanical energy into electrical energy. An external energy source, such as a steam turbine, turns the armature coil in a magnetic field beam. The wires of the coil cut the field lines, and an EMF is produced, a setup, which is equal to 2 pi, the number of turns, the area, the magnetic field, and the frequency of its rotation, then cos 2 pi FT. So this EMF is induced between the terminals of the coil. N is the number of loops. Okay, I've said that. And A is the area, F is the frequency of rotation. So that's the formula. So how does an electric generator operate? How does an electric generator operate? So this is like we had before. These are permanent magnets. This is the north pole of this magnet. This is the south pole of this magnet. And we have this rectangular coil there. You have your AB, you have your CD. In this case, the rotation of rectangular coil in a magnetic field results in a voltage output, whose polarity reverses with each half cycle. So these are the split rings like we had before. It's rotating with the coil, and these are the brushes which are fixed, B1 and B2. And you can see the direction of motion, you can see the field direction, you can see the rectangular coil which is rotating in this direction. And this is the shaft, this is the axle. The ends of the coil are connected to an external circuit by means of a split ring. Oh, sorry. So the ends of the coil are connected to an external circuit, which is not shown, okay, an external circuit by means of split rings and brushes. So it's connected to an external circuit. For a current to be induced in a coil or a wire loop, the magnetic flux through the loop must vary with time. So for any generator, the input mechanical energy is equal to the output electrical energy plus friction and heat losses. The losses are only a small fraction of input energy anyway. So, this is another worked example. An AC generator produces an output voltage of which is equal to 150 sine 367 T, that's time, and volts, where T is in seconds. What is the frequency of the AC voltage? What is the frequency of the AC voltage? So using the formula given earlier, we have 367 T as being equal to 2 pi ft, from which we find that the frequency is equal to 58.4 hertz. So you can try it and see whether your solution is the same as this. This is not detailed, but it's just a hint for solving the problem. So a sine curve plotted as a function of time is not different from a cosine curve, except for the location of t equals to 0. So if you use this formula, you get your frequency to be equal to 58.4 hertz. So try it out and let's see if you are going to get the same answer. So I'll give you a minute to write it down and try and work it out. So there's another example here with a hint given. A hint is also given to the solution. It says, how fast must a 1,000 loop coil, each with 29 centimeters squared area, turn in the Earth's magnetic field of 0.70 gauss to generate a voltage that has a maximum value, that is an amplitude of 0.50 volts. The hint is that we assume that the coil's axis is oriented in the field so as to give maximum flux change when rotated. Excuse me. So a hint is given to for the solution. You have the formula here. Then because cos 2 pi ft has a maximum value of 1, the amplitude of the voltage is equal to this, where B is equal to this. So it says, how fast must a 1,000 loop coil turn in the Earth's magnetic field? Sorry, there was a disconnection. So back to the topic we were looking at. It says credit or debit card readers. How do they operate? The electronic card swiping machine or card readers machine is based on the principle of electromagnetic induction. So any credit or debit card has a magnetic strip on the reverse side of the card called mark strip. If you have noticed, when you take your ATM card, you notice that it has a magnetic strip on the reverse side. So the mark strip is made up of very small magnetic particles, about 20 millionths of an inch, and they are aligned in north-south direction. You might not know. All you want to do is pick up your ATM card and get your money, okay? But this is the physics behind it. It uses the principle of magnetic induction. So this is a picture of a card reader, and this is the magnetic strip as a bar magnet inside. This is the way it appears. See the North Pole, the South Pole, the North Pole, the South Pole, the South Pole, the North Pole. This is the way the strip is arranged in the mark stripe. The magnetic stripe, or called mark stripe, which has varying magnetic field orientations along the length of the card, is swiped through a card reader. A change in magnetic flux is produced in one direction. This creates potential difference as the card, which has varying magnetic fields, is passed through a card reader, which is a pickup coil acting as a closed loop. So when the card is swiped past the magnetic head on the card swiping machine, current is induced, and this current triggers the information access stored in the respective registers. So according to Michael Faraday, changing magnetic field induces an electrical field. And that is the principle by which the card reader works. I'll just introduce transformers today. Oh, what's the time now? Because I want to stop around 10 minutes to 9. I have another meeting. I have a meeting. So next class, we are going to be discussing transformers. And after transformers, we'll be discussing AC circuits and all that. So let me look at your solutions. Let's go back. Or if you need time to write this, I can leave this on for you to quickly do your classwork. If you've not, because if you submit outside 9 o'clock, I'm not going to accept your solutions. So your solutions should be submitted before 9 o'clock. So I'm giving you some few minutes to look at the worked examples again. This is the last work example for today, example 6. If you haven't written it down, you write it now and begin to solve it and send your solution as a message. And worked example 5, this is worked example 5. This is worked example. I'll just go over the worked examples. This is worked example 4. And worked example 3. Worked example 2. And worked example 1. So I'll be expecting 6 answers from you. Not necessarily the process, but the answers. And let me look at some of the messages. Chats. Oh, good. Somebody has already sent the solution to, oh, work the example 5. The solution has already been given to you. Somebody has sent that as answer to question 5. Well, that's okay, but you need to be sure and to confirm that that is what you got. The answer has been given to you, but you need to confirm that that is the correct answer from your workings. Okay, somebody has sent that. I think this is a convenient point to stop for today. Gradually, we'll get to I wouldn't say no, it's not a physical class. I would have said we'll get to know each other more. But well, your test will be taking place next week, Wednesday, and it's going to be physical. It's not going to be online. Please don't stay at home and be expected to do your test online. Come to UI, come to physics department to do your test, and it's going to start by 8 a.m. So that means you have to be at your venues, different venues, by 7:30 a.m. By 7:30 a.m. with your writing materials. You are not supposed to take your phones into the exam test hall. You bring your pencils, your sharpeners, and your erasers. There's no borrowing. Physics department, you don't allow students to borrow things during tests or exams. So your CA test 1, you are going to be having 2 CAs as you have been told. CA test 1 and CA test 2. So this CA test 1 is going to be based on what you have been taught. So what you have been taught so far by my colleague, Dr. Shakwande. So the questions will come from, I'm sure he has told you, he must have told you that. Or do you want to talk to them? Okay. So there will be 10 questions to be answered in 30 minutes. Oh, 20 minutes, 20 minutes. You have 10 questions during your CA test 1, taking place next week, Wednesday. Next week, Wednesday is 30th, 29th September. Pardon? PHY 104 and 105. PHY 104 and 105 will be taking place next week, Wednesday. So don't come late. If you come late, you can imagine a test of just 20 minutes and you are 30 minutes late to the hall. That means you'll be missing the test and it might not be repeated. It's not going to be repeated. So I wish you all the best in your test. See you on Monday, 8 a.m. by the grace of God. And I think there won't be any interruption, hopefully. Thank you. I think I'll say bye for now.